Hello?
Hello.
How are you?
Not bad.
Good. Yeah.
Just in the car, but just getting to the lab. So
Oh,
the
okay.
the trains haven't started yet in San Francisco this
Oh, yeah.
early. So
Yeah. Jesse, how are you? All right. So welcome. Why don't we get started? I'll start with talking about the meetings for this week. There was no DevoWorm meeting, but and that's because one of our longtime collaborators died last weekend. It's Richard Gordon. He was an integral part of the beginning of DevoWorm, and I'm going to do a memoriam to him at some point soon. I'm working on it right now, and so that I'll put that up on the DevoWorm YouTube channel. In the meantime, we'll have a meeting next week, but I wanted to take a week off, just to take a break from that. So we did have an open source meeting as well as a Cognition Futures meeting. So Cognition Futures meeting was quite interesting. We had, and Jesse might talk about it later, Jesse actually had some slides on a paper that we wanted to talk about from our special issue on, I can't remember which paper it was. It was a Michael Levin paper on, we'll have to refresh my memory on it. I don't know if Jesse still has the slideshow, but maybe we can look at it a little bit more today. Yeah, it was the topological constraints on self-organization. That's what it was. Okay. But we did have an open source meeting, and the open source meeting was really interesting. So let's get to that. So our open source meeting, there's a Shu and Jesse and myself. And Barshan gave an update on his work. So he's been hard at work with the Google Summer of Code coding period. And he issued a pull request last week, and he's going to issue a pull request this week. It's on implementing his attention mechanism for graphs, or graph neural networks. And he mentioned that he did a blog post on the attention mechanism and networks, but he couched it in terms of like social networks and like some sort of social situation. So, that makes it a little bit more intuitive for people to sort of understand what's going on, which I like because, we do have that science communication aspect to the lab. So I'm going to try to cross-post that to our Medium. It looks pretty good. But he also did another pull request last week on some of the attention mechanism code. And he had mentioned that he needs to fix some bugs in it, update that pull request, which is fine. And then maybe do some other types of testing. So, we're getting into about week 3 or 4 of the coding period. So this is where you start to get you try to make sure that what you're implementing works. So he's right on target. He's doing pretty well. Okay, so we have Barshan gave an update, and this is his post. The 3 modules explain like a school network. This is where he has his EAM mechanism, the friendship rater, and then he goes through, he talks about this DRL, which is the relationship tracker, So DRL is one of the components of his model. So EAM says in the embryo, which he talks about the social setting and then back to the biological setting. In the embryo, EAM takes a three-dimensional cluster of cells at one specific minute and assigns high attention scores to the physical cell-to-cell contacts that are critical to the embryo's shape in that moment. Then he has this method called DRL, which is the relationship tracker. And his tagline here is history matters. How did these relationships evolve? So this is looking at the relationships in the graph over time from the previous time step to the current time step and then updates in future time steps. And so he talks a little bit about that. And he says, in the embryo, DRL takes the structural map from the previous minute and updates it with the new EAM map. So the model understands how cell relationships evolve as the embryo grows. Then finally, he has DNL, which is the personal growth updater. And this is, again, DNL, the personal growth updater. And the tagline here is, given these relationships, how does each individual change? So now that you have your topology here, actually you have your topology back in the EAM, and that's kind of determined by looking at which friendships hold everything together right now. And the topology changes, but you have to have an account of how those entities are connected. And then the next thing is to update this over time and understand what the structural map of the network is. And then finally, this last part, which is given these relationships, how do the individuals change? So you're looking at the individual nodes and how those change. So, this is where in development we have cells that divide. And so you might have at one time a cell, and then that cell dies, and those connections are removed, but it doesn't actually die so much as it divides, which means that you get two cells instead of one, and they might move to new locations, but there's a history there of the previous cell. So this is DNL, and then let's see if I can find the sort of the biological analog of this. In the embryo, a cell's biological state, gene expression, signaling activity, or other features changes based on the neighbors it touches. So these different things going on in the cell, the constituent components, change based on the neighbors it touches. DNL updates the cell's mathematical profile to reflect those biological changes. And then he says, he has this part where he talks about how the flow works together. The first point here is that EAM takes a picture of cells right now and says, these physical contacts are the most important. DRL looks at this picture and says, based on where these cells were a moment ago, here's how their relationships evolved. And then DNL takes those evolved relationships and says, because the cell is now touching these neighbors, its internal state has changed. So that's how this works. And then this is part of a larger flow of SGEL, which is the method that he's using here. So this is a clean version of SGEL's story. First identify the important edges, then learn how those edges change through time, and finally update the nodes themselves based on their new relationships. And so this is really kind of according to Barshan, this is taking development into account. So we talk about things like developmental AI, where we have these analogs of development, where we might train a model in different ways, or we might alter the network in different ways. And that's what he's trying to capture here. And so and he's making the analogy to social systems. So, yeah, that's the story I want to tell this week. SGEL. That's the story I want to tell this week. SGEL is not just another graph model. It's a model that thinks like a growing school where connections matter, relationships move. and individual cells keep changing because of the community around them. So that was his presentation on SGEL and some of the things he's doing. I thought that was a very good way to summarize it. Okay, so then we talked a little bit about that, and we always kind of get into the thing that's being presented in the meeting. And Ashu also mentioned that she was working on her open source project, and she'll be submitting. So she's created some different things and posted them to a GitHub repository, and she's going to be updating those. And so her update, I think, is coming next week. So I look forward to seeing that. Okay, so then I talked about this topic that, I always come up with these really eclectic topics for the meeting. And yesterday I talked about open source frontier AI models. So, the idea is that you have these frontier models that all the large AI companies are working on. And, they're usually these large models that have been sort of vetted internally, have very large training sets and are used in a certain domain of knowledge. So we have frontier models for different things. We have frontier models for image segmentation. We have frontier models for neuroimaging. We have frontier models for a lot of different areas. And so the idea is that, you have these companies create these frontier models and that they can maybe make a profit off of it. But it also restricts people's access to being able to modify their software. So if you think about the neuroimaging frontier model, if you have a large corporation handing a frontier model to a series of neuroimaging teams, they have those tools available to them, but they can't necessarily modify them the way they would like, or they can't necessarily use them the way they would like. It's a bit like proprietary software. Like if we had a copy of Photoshop, we can use it, but we can't use it maybe the way we would like. Or we have this licensing barrier where, we have to pay a certain amount of money to maintain our access. And if we don't, then we really have no workaround. We're stuck without having access to that model. And this has been a practical concern for organizations, especially small organizations, for years. How do you build infrastructure in your organization? If all the tools are proprietary, you have to pay everyone for access, it becomes onerous, and you can't stay competitive with other such groups. So this is not just an issue of ethics and things like that, which we did talk about, but it's also very practical. And so the one way out of that, of course, are open source models, where you can give people the means to, maybe build their own models or modify their own models, or have something that is, at a more reasonable cost or even free. And then, you have some restrictions on how it's used, but otherwise it's, something that's maybe more viable for small organizations. So this is where we talked about the recent trends in open source models. Now, open source models in like large language models, which we mainly focused on here, traditionally they've been behind the curve as opposed to proprietary models. The open source models, have kind of lagged in their development, and for good reason. I mean, you think about the proprietary models, companies are putting a lot of resources into those models, and the open source models are sort of playing catch up. And, sometimes like companies like Meta, we talked about how they will release a proprietary model and an open source model. The open source model maybe not being as, complicated or ornate as the proprietary model. Nevertheless, the open source models are catching up to proprietary models. And from a practical standpoint, they offer most of what you need. So we talked a little bit about open source frontier models and why they're essential components of what's going on right now. So, as open source models are reaching frontier level performance, this is becoming, kind of a thing that people are paying attention to. And so this is where we get into, things about open models closing the gap of performance, and how, there are many, many open source models out there. They've proliferated, and of course, now you need to figure out which one is best for what you want to do. And there's so many open source models. DeepSeek has a series of models. QN has a series of models. Meta released a number of models under Llama. And so all of these things are available to people. Mistral has a number of options. And so these are all things that, you have to kind of figure out how they work and, benchmark them on your own data sets and so forth. And so another thing we talked about is, besides the benefits, you have to think about sort of the drawbacks of open sourcing models. So if you open source a model, first of all, it depends on what you mean by open sourcing. So sometimes it's just making the weights available, and so sometimes that's enough for people. Sometimes it's making the whole architecture available. And so depending on your needs, you would pick an open source option that suits you. On the flip side of that, you have concerns about, whether or not you even want to make the entire model open source or available to people to modify. And this brought us into this idea of licensing terms, where you have, you specify how people can gain access to the model, whether it's just the weights or the architecture or whatever. And there are a lot of sort of national security concerns and a lot of, proprietary concerns. So some of these organizations are actual companies. Some of them are, nonprofit organizations, but they have a community where the community, they want their community to have a certain standard of conduct. And there's an imperative there for control. And so there is this aspect of controlling access to open source models, even though we don't think of that as an imperative. And to underscore that, we talked about the history of FOSS, or free and open source software, and how the idea is that, it isn't free in terms of free beer. It's actually more free in terms of free access. But then, the idea isn't really that you just provide access to everything. It's that you provide access to certain components, or you provide access, the level of access is specified by the organization. Which in itself is both good and bad, because you can end up sliding down the slippery slope of green or open washing, where, you say you're open source, but you're really not. So OpenAI, for example, is, it's not necessarily open in the way we would think of open source. You use an API to communicate with the model. So there's no transparency there. There's no control over the model. You're just using, it's almost like you're querying a black box. It's almost like the Chinese room experiment in cognitive science, where you put a message into a box and you get a message out, and you don't know what the process is inside. And it's kind of one of the problems with, when someone says something is open source, or when you have a situation where, you want to go across to open source organizations and compare tools, you also have to think about how they're actually approaching open source. What is their philosophy? So we had a really robust discussion about this. And so we really went through and had a lot of things to say about this. A lot of things that tied in, I think, to AI, like AI ethics, and some of the things that we're doing in SET, Society, Ethics, and Tech. And, it was very, very exciting. Then I had another article on sort of the economics of frontier models. And this is an article, Open Source and Cheap Frontier Models. And this was an infographic from the article where they kind of go through some of the different models, some of the different approaches, this open AI spectrum where we go from proprietary black boxes all the way up to open everything, basically. And how infographics tend to be is they tend to be very stereotypical, so they don't get into a lot of the nuance of some of these things. And this one on the right here for understanding the OpenAI spectrum, it says open weights unlock data sovereignty, which is not entirely true, but I know what they're trying to get at. So they talked about this open spectrum from completely closed to completely open. They talked about different strategic actions for enterprise users, which, we talked a little bit about enterprise users versus non-enterprise users. And enterprise users are usually, organizations that have money. They're very, usually large organizations that have resources for, say, implementing these models. And smaller organizations or non-enterprise organizations usually don't. The ops part of the DevOps is not very well structured in these organizations. So you try to implement a model, and oftentimes you have to jump through a lot of hoops. Not only that, but you have to then kind of spend a lot more time implementing a model than you otherwise would. And this is, something that in your proprietary models usually get some sort of support with, or the models are made to be easily deployable. So this is one of the sort of the trade-offs of open source models versus proprietary models. And then talking about some of the methods that are being used to reduce costs. So models have dropped in their cost in terms of training and in terms of implementation. And there have been a number of methods and other things that have converged to make these models cheaper by and large. So if you're training a model, it used to be much more expensive to train them. Proprietary labs spend much more money on training. And this is a graph, I guess, where they're showing a proprietary organization where they have a higher amount of money spent on training, and then their API costs more. And with DeepSeek, which is they use as the open source example, the frontier AI training cost is decreased by over 95%, and then the API pricing correspondingly drops a 10 to 30 fold reduction of that number. So we have, this is kind of a very busy infographic. We have a lot of things to consider, and we think of this distinction between open models and proprietary models. So and then Jesse had a couple things to say at the end, and then that was the meeting. Okay, so that was our open source meeting. So yeah, that's that. Those were our meetings for the week.
Yeah. Very quickly, I don't know if you can pull up the Hussein's LinkedIn post. That's great. I wanted to do it. I don't know if I can do it easily right now. If not, we can cover it later in your memorial. I'm not going to spend a lot of time on it, but just even just a moment on Dick Gordon. Just I I I I really respected him in the sense of I wasn't even as close to him as many of you all were, and certainly Hussein and other folks in Diva were. But just it was really great to see him as a really positive older role model mentor figure in the space. He was always reaching out positively towards me. Hey, if you want to work on this, you can do this, or you do this, or it was a really just a great presence to the community. And even as someone who wasn't close to him, it was inspiring for me as like, oh, like it's great to just see that modeled. So I can certainly speak to that, and that's just one very small facet that I saw. So I definitely miss him in the meetings. I kind of thought he might he wasn't around as much, and starting to like I was starting to miss him in that way even then, and hearing the news is very, very sad. But I'm glad to have known him, and I look forward to the memorial. And if I can contribute to that, let me know. But I'm sure there's a lot to say, and I just wanted to say my brief comment about that. Um, that said, uh, this week has been a really, really busy week for me, with a few interesting things. Bradley just covered Friday the open source summer cohort, Google Summer of Code, which is going well. I'm very curious. Uh, Barshan's doing great stuff, and I'm very curious to see Ashu and is it Kavya? I think is also wanting to do stuff. I don't think I don't recall that he presented any of his work this week. He has made some recent, um, like the document that he's made about like it's kind of Bratenberg vehicles, active inference type stuff. He didn't mention that anything about that Friday, right?
He wasn't in the meeting Friday, but yeah, I haven't heard about it on Slack either. So
Yeah. It's that's what I thought. I mentioned it because um there's a there's a few things in there's a few very, very, very far removed slight tangents in data and direction, which I might get to in a moment. But also just some of the multi-agent approaches that Avery has talked about, and I don't I didn't see Ashu's updates from GitHub or what she was looking at. But I think there's a lot of interesting things there, kind of tapping into the brain vehicles, maybe meta brains type stuff. So I'm curious about that, just to mention that before I forget to move on. You mentioned Cognition Futures. You reviewed the topological constraints paper, um, which, oh yeah, um, I'm not going to totally review. It was, it was a very, I might almost make a separate posting about it because I felt like we loosely did the paper justice in the meeting. Um, I actually think I think the core thrust of the paper is, I guess I happen to easily have it here, so I'll put it on here. The core thrust of the paper, actually, this is better this way. Um, was trying to get at why inherently models, as in LLMs, really will inherently drift, like structurally, thus the topology. I don't know why. Uh, the nature of the design of how the interactions are taking place themselves will eventually break, and they're using the specific examples, which probably Bradley can comment on more in depth if he so chooses. Um, Specific examples, and saying how in these sort of fixed context window spaces, there's an inevitability and limitation in, let's say, the dimension. It's like they basically saying the way things work right now, or have worked in most of how these have been designed, is essentially things are too flat, and some of the inherent relational uh, relational information, or I want to use words like mechanism, but that's really not the right word to use. The topological structure of other things, and that biological systems maybe are a little bit better at handling in these cases, is related to why the structure is related to why these models are unable to uh, ultimately hold a specific context across time. Um, we discussed the necessary conditions on topology of the graph in ordered phase to exist with an eye towards finding constraints in the ability of a system with local interactions to maintain the target states. They look at these three model systems, and as an application, they analyze why multi-scale systems like those in biology are capable of organizing into complex patterns, whereas these rudimentary language models are challenged by long sequences of outputs. And so the big caveat to their paper at the end is them basically saying, well, this is what we're looking at, but it's somewhat of a, I don't want to say too special of a case, but they open that they very much mention that, well, in the way things are going, we aren't fully where if models change in this way, then some of our ideas with limitations may change as well. Like the dynamic ability to change context windows and do more in that. More advanced models in the frontier of them and where they're going may change their suggestion that there's a limitation there. But it was interesting because the discussion was it led to a lot of discussion about Avery's work, but it, I think there's something it's one of the more, I don't want to use the word like accessible, because maybe it wasn't. I think many people in the reading group were like, well, I kind of get this, and a lot of like some of the deeper math physics examples might be a little bit too deep in the weeds for some folks to really grasp, and I'm certainly say I didn't fully grasp everything either. But I think there's something of looking at the nature of topological constraints in the classic, in the 1943 paper sense, like in this, like I think there is, and by this I mean this here, I think there's something to, I'll put it this way, if this is maybe my approach with other things rather than Cognition Futures right now. I think a more robust, like taking the premise of this paper and making it a bit more robust. And I don't know if Sacco and other folks will be doing that. I think it's more of I think it's kind of their work, and then like Levin's twist on it in the world model sense. But I'm very curious to see what would a much more robust cataloging of these topological constraints be in the context of this, in the context of, regardless of regardless of the complexity, both machines, living organisms, substrate independence, I think was sort of one of the key terms that came up here. It's not here, but phase transitions, yes, emergence, etc., and these sort of topological constraints, and that as a oh, sorry, I was looking at the keywords here on this, but they aren't. Top substrate independence isn't there. I think there's something. I think there's absolutely something that a more mature model of, let's say, cognition, or what this is trying to get at in a substrate independent way, in a embodiment agnostic way. I think there's some very important things that this is trying to get at that it was sort of gestured at here, and this does a nice job of trying to, I think, identify the limitations. Like maybe it's because of my limited ability to grasp the paper, which I'm very open to acknowledging. But I think in some ways the limitations of the paper are like the limitations and the future conclusions of the paper, and they talk about you know where they want to go with it. I forget where it is, but I think I think it was a I see it much more as like what the paper's trying to gesture at in terms of potentially cataloging those things is quite interesting. And I don't know that we really got to cover that as much as I wanted to in the meeting. So I'll leave it at that and open to any comment if you guys wanna say more. But that was sort of my it was like my I have this sort of intense afterthoughts about the paper because we didn't really get to address it, but it's hard to address what I really wanted to address. So any thoughts or things about that? Yeah.
Yeah, let's look at the paper a little bit. Maybe some of the figures. Yeah, there are a lot of figures that are like, you know, context-free networks, to put it in a charitable way. So you have like, a network, and usually we draw these out to characterize interactions. But in a sense, what does this mean? Like, what does this mean? Like, say, in the brain or in a social setting or whatever we want to make into a network. So it
Mm.
just really represents what the interactions are, and we're very selective in saying what those interactions are. Right? We know, like, say, if we're building a connectome, we have interactions, maybe chemical interactions or electrical interactions. We also have a lot of signaling interactions that are driven by peptides or by proteins or other things that we don't put into the model. So we consider those to be sort of noise, but then we focus on a set of interactions that we're interested in. In social interactions, we usually maybe focus on, like, if I send a message to you and you send a message to me, but we don't focus on maybe like if I can see you in your nonverbal communication, or if I can like have other context cues. We don't put those into the model. So it's interesting that we have that sort of very high level of selectivity. Yeah, and the same thing happens with a lot of these sort of grid models, where you're looking at something like this, where you're looking at interactions between cells or grid constituents, and you're using that to sort of characterize higher order collective uh, behaviors. So if I'm interacting with you and you're interacting with me, we can synchronize our behavior and we can become this sort of block on this graph. So, I mean, and they're very highly selective things, but then we also talk about networks, or in these kinds of models, like these models of grids, that there's some universality here. So I can go between social systems and biological systems and other like physical systems, and it basically behaves the same way. So it's interesting to think about that. Like, we're making a bunch of design decisions in our analysis and saying these are the
Mm.
things that count, and everything else is kind of noise or not as important. And then we're saying, well, really, if we do that, we can get these universal effects, or we can boil it down to these things that every network has. They have, sometimes you have small worldedness, sometimes you have like, they talk about cliques in this paper, which are these tightly bound submodules of networks, and all these things. You see these in every type of network, and the question is if you can sort of characterize connectivity and characterize these behaviors of networks, then you can benefit from things that we've seen across all sorts of networks. So, I mean, they're really kind of going all in on this universality aspect of, these types of networks, and then, linking that to intelligence and other things like that. And so I think that's, it's a fruitful approach that you have to keep in mind some of the things that you're kind of, the assumptions you're kind of making here. So that all these models, they're very abstract in a very utilitarian sense. They have to be abstract to see these kind of universality features. And then this other aspect about sequences and autoregressive sequences. So this is like where you're getting at, like he's talking about the sequences in development here, or regeneration, where you have a bunch of events that happen, and they have to happen in a certain order to be successful, or there's usually a process by which something unfolds. So in regeneration, if you have, like in this case, some amphibian gets its tail cut off, then the cells respond in a way that's like this basically autoregressive sequence space, where they kind of collectively organize, they figure out where they need to be, they get recruited, they go to their location, they de-differentiate, they fill in the space, and then they redifferentiate into a tail. And you can think of maybe like a large language model in that way. I mean, there's a sequence of events that unfold, but there's also these sort of parallel interactions that happen among cells, right? Because cells are in these populations, and they're kind of communicating and prioritizing their movement, their migration, and things like that. And you end up with this pattern formation, very quick pattern formation, that is otherwise maybe not the case. And it's interesting that, like in a lot of models of regeneration and of morphogenesis, you know, um, the assumption has always been, well, there have been two schools of thought here. One is that there's this self-organizing process where there's this sort of parallel set of interactions, and then there's been this other set of this other school of thought where there's like a template, and so you have a, like, maybe you call it. It actually goes back to the ancient Greeks, preformation versus epigenesis, or like preformation being where you have like a little model that is applied. Maybe like you have a little model of the organism that gets like reproduced, versus like a model of self-organization, which is basically what epigenesis is. And so this has been a debate for centuries about which one explains the data the best, I guess you could say. And it seems like there is this, epigenesis is what is the case, and it makes this parallel between language models and writing or text, and then morphogenesis, which I think is really interesting because of course text is sequential. It doesn't have a lot of parallel interactions, although it does, because if you're reading a book or you're reading a document, you don't often read in sequence. I mean, you do read in sequence to read it out, but to understand it, you have to go back and forth between different parts of the text. And you of course use information that you've learned in other texts. So there is this sort of these parallel interactions there. And then you can make sense of the text. So that's really interesting. And then describing it in this way, in the mathematical way, in this sort of universal way, is interesting.
Yeah, and I'm reminded of the work of Elon Barinholtz, who's really trying to champion some of this take on autoaggressive stuff. I don't want to get into it right now. I know Elon has a preprint that's out, which I really haven't looked at fully, but I feel like one of and this can be a transition. I don't know how much. Is there more you wanted to say about the paper overall, or were you ready to move on before I make any segues?
I think we could move on. I don't know.
Okay.
Yeah.
I'll make a very loose segue to this. We for next week, and we're doing another paper. I forget which it is specifically. I might be able to just to see it here. But as I looked at that in this within the same volume, I think it was the goals one. I think it was goals and structure.
Yeah, I think it's
With Amir and company. My segue is, and this came up interestingly in data and direction, which is going to be where I'm going to next. There's one of the things that I'm seeing overall, and this is actually quite a big deal, if I may say so. I find myself in conversations that I'm having at large with people dealing with large language models and I think there's very specific terminology for this that if it comes to mind, please remind me of it. But this thing that's coming up is essentially applying the language of things we know very well as humans, in and saying like we're kind of putting upon the system particular characteristics that it's giving us trace resemblances to. So maybe less so with this paper about autoregression and topological space. Like it's trying to approach from what I appreciate about the paper we just looked at was that I do think creating basically in incredibly simplified terms, do I think it's a good idea to invest in topological constraints as a useful lens to trying to understand some of these different things? Yes. I would like more of that, please, in a more rigorous, more cataloged, more in-depth way. I think there's something there. Now, I know this is a bit of a potential jump, but in the same way, one of the biggest things that I don't think that we've talked about it substantially here, but they're probably going to give me some stupid ad thing about this. I'm waiting for this to load, if it's going to load. One of the things that we've been talking about, and we won't have to cover this, is very society, ethics, tech related, or I want to say coded. Okay, here we go. Is this video, which I don't recall that we have spoken about it at length, and at least in the Saturday meetings. The video is a very interesting discussion between a older lady who is a mother and her son. This is Celeste on the left. This is Ernie, her son, on the right. And it talks about her, I would say, above average informed level of discussing her quote unquote relationship with Max, which is ChatGTP like 5 something, right? And I watched this video in different contexts. I watched this video with Jen of JoPro, who's mental health perspective. Jen's also a social worker, grad student. Have discussed this with other folks in different ways. And without getting into the details of it, I'm mentioning here because it's really pressing upon me lately that across domains, we don't quite we're using in my personal opinion, very inadequate terms for what we're trying to look at. So we have these things that are like as I'm going through these different spaces, I think there's a broader language to be developed that is about what are principles that hold or that are substrate independent, but at the same time focusing on, let's say, focusing on things like mechanistic or structural constraints is one thing, and then coming to a situation where what the human is doing with another with a model maybe should have its own unique language and taxonomy. I'm coming up with different terms for, you know, it why is it so easy for us to say, oh, in a relation, she has an AI boyfriend? All right. Another way to say that is, as we came up in discussions this week, she has a projection of herself interacting with an AI model has become this entity that she's trying to relate to in a particular way. And I feel like those are very different frameworks of, are we using language of a human being interacting with another human being and having a mutual, autonomous, interdependent relationship of some form? And again, when I mentioned this at one of the MIT AHA seminars, one of the people was like, "Oh, well, I don't know about creating terms for human AI interaction because I'm not even sure what to make of labeling human interaction in particular ways, like labeling the relationship as to ways like maybe I'm not so sure about that either." And I was like, I get that, but at the same time, I think I think I think there's something quite valid, at least in my opinion, still, to identifying what type of, not being incredibly cautious, even as we're trying to reach for substrate independence, even as we're trying to reach for things like these general principles, like the tension between trying to find general principles across variations of experience versus and especially with the LLM and autoregressive stuff and the things that give us the, oh, we can interact with it in a way that spits out text and shows its thinking in a fun, like because it's doing that, that doesn't mean you now have to use the language of it's communicating at you. One of the things that's come up a lot in DigiNest and a little bit now in uh, data indirection is like the idea of like giving a model's output human characteristic traits, and like especially things in my opinion, like calling a generative AI model's output honest or not. Like at one level, I get what it means in the way, like, oh, Jess is talking in an honest way, Morgan's talking in an honest way, Bradley's talking honest, he's speaking honestly. And it's like, how do you there's a certain implication of a model having there's a certain implication of a model having the capacity to be dishonest. And so like we're using these traits and these associations, these sort of human social things to try to like label or determine or whatever. I find an increasing amount of tension there, and I feel like I want to continue to articulate and expand upon that tension as well as I can, because I feel like negatively, I don't want to just be a purist. I think I don't want to be a purist, like, oh well, it doesn't have it's not conscious, so therefore it has no means of choosing between being honest or dishonest, so therefore it's not a useful lens. Like, I think there's some usefulness even of that angle, but also getting to the specifics of what we want to study is really going to put pressure on the fact that we don't have these alternate articulated frameworks to look at some of the things, and that's where a lot of the work is now. Like a lot of people are doing work in that space, but I don't know. I wanted to mention that as a broader recurring theme that's not so much in the Saturday orthogonal lab things, but it's coming up in a lot of different areas, and people are coming in and asking different questions that kind of keep bumping up against this. So maybe we'll do something. I actually have a long-standing discussion with Jen about this video that really raised some very interesting points that we may hopefully publish soon. Just a sort of a we have a modernizing mental health discussion series that has many different entries that are not fully published yet, but have been recorded and will be out at some point. But like in any, and I'm going to mention very briefly some data indirection things in general. But I know I said a lot of things that were gesturing at stuff, but any comments or questions before I go into some other data indirection specific things?
I don't have any questions.
Data indirect, we had a full week of everything, and people are getting their projects in order. We have some interesting looks at policy. We have someone looking at the reflection agency framework, which we talked a bit about before. There's also a set of people that are interested in looking at specific things in Anthropic at a policy and an economic level as well. So I'm very happy to see where that's going. And it's very interesting to see people stepping into the space and kind of collaboratively trying to build out what we're doing with that program. So, and we also have someone that I'm so glad I remember this. Yeah, one of the people has a fairly direct. I meant to mention them in the Cognition Futures meeting, but Violet's actually someone who has a history in cognitive science, and her approach is going to be, she's the most like cognitive science oriented person in data and direction right now for our summer cohort, but she's going to be looking at Julia Haas, who's looking at moral competence in language models, or at least that's her starting point. And she's read a few of her papers and has some experience there. So sort of this cognitive mechanisms behind, kind of what a different angle of what I was getting at a little bit, but moving beyond evaluating the mere performance, the ability to produce morally appropriate outputs, to evaluating the moral competence, as in the ability to produce morally appropriate outputs based on morally relevant considerations. So this is a bit more of I think Haas is with DeepMind, and it will be sort of this looking at these challenges, facsimile problem, moral multidimensionality, and moral pluralism is very sort of this what can these models actually afford us at, I would say, a technical / cognitive mechanistic level. What can these models offer in terms of moral moral competence, and moral competence in how do we get to a place of having the means to evaluate the moral competence of these generative models. And I find it to be both interesting and like to put on my I'm very happy to be doing that work, or have someone looking at all this. And on the other side of the coin, I have this strong sense of there's many quotes to mention about offloading decisions to machines, and then it's, well, who controls the machines? Like the difference between the the moral capacity of a AI model, if you will, or the moral competence as is being said here, versus there's a very unsettling thing that I know Norbert Wiener and other people, and many other technological ethical people have gotten at, which is the specificity to which any machine precision has in terms of deducing anything is also simply the means the fine grain that someone controlling the machines can steer something to do. And that's sort of the double-edged sword of all of the things that we're doing in a lot of ways. But outside of that, even, it's sort of like I personally have a lot of reservations about calling generative something which generates a output in the way that I understand the models to work as having, like, I think there's a very fine criticism of how can you, like, where's the line between anthropomorphizing what's happening and saying these models are doing, you know, saying the model has a particular quality that we're looking for. So I already went into that earlier, but I will, I don't know, that trying to be articulate about that on many fronts right now, and seeing where that comes with this new cohort that's very in the things they're interested in, and putting them together in a group to talk about it across time, as complemented by Cognition Futures, as complemented by DigiNest, is a really interesting. It's personally quite interesting to see these different groups trying to wrestle with this stuff. And I will kind of close by saying, I do kind of want to try to, I know we mentioned this a few weeks ago, but like some kind of an end of summer showcase event, synthesis event, where we're all kind of talking about what we're doing. I think it would be quite fun for the summer. And I feel kind of both privileged with the vantage point that I'm seeing from these different discussions, from the technical to the whatever I was trying to say, with like the lack of language or terminology, to the different domain spaces of like policy, and then we have like the Cognition Futures world model technical type approach, cognitive stuff. I feel privileged because I feel like, okay, like I want more people to kind of have the vantage point that I'm being able to see here and talk about it, and the pressure of like, oh, there's a lot to do here. So yes to the showcase event, hopefully. And then very briefly, I'll say there was also a DigiNest meeting today or yesterday. Avery was supposed to be well, Avery was supposed to host it themselves. I don't yet know fully what happened because I was away at another event. I loosely called it a Joe Pro social event. I was in downtown Boston. I tried to make it somewhat social precursor, because a lot of things going on in Boston. It's a World Cup, so a bunch of the Scottish fans were particularly present, and I heard various music, I saw various kilts, and it was fun to ride the T, which is a local subway here. But the social event was also about seeing a play, or not a play, theater, Les Mis, at the theater house there, and the opera house. And it was a very good time and fun, and just a nice, somewhat generic social thing to do, and it's good to be out in the community. But I was not at DigiNest because I was sort of loosely hosting that. It wasn't a big giant event in terms of, oh, we have a big party, but it was a fun night, and it was fun to be in Boston. And I'm trying to make as much as possible certain, like, hybrid or in-person meetings when we can. Last thing I'll say about that: in a few weeks, Molly from DigiNest will be here in Boston for, I think, a neuroergonomics conference. I think we mentioned this some time ago. So we may try to host something on one of the Fridays that would be like a very interesting in-person, for sure, and then maybe a hybrid event on that Friday or that Saturday if Molly and folks are still around. So to be determined about that, but that's my social event end cap to my session. So any comments or questions, or we can move on to, I'm sure Beverly has a bunch of other things to get to today.
Are you able to hear me?
Yeah.
I can hear you more.
I dropped a link to an old project that I had started at the beginning of kind of my agentic coding. It's very relevant to the paper, so yeah. So, it's like, I don't know if you remember this, like months ago, but I was talking about Ising models and like social interactions modeled with statistical mechanics, and yeah, so there's they don't take a very computational approach. They're I get the feeling it was written by a mathematician.
Yeah.
No judgment here. But if you're interested in if anybody's interested in kind of computational experiments that of the same vein, this is the package for it. It's all in JAX, so it runs very, very fast on GPUs. If you do have some larger models or more complex interactions that you want the models to have. And so sorry I missed the meeting. What I'm gonna do is I'm gonna try and drop some of the paper's ideas. I'm gonna incorporate them into the package with demonstrations. Excuse me. So that you can, so hopefully demonstrations. Now, I'm not sure that the claims about LLMs are seem to be the least supported or the wildest claim in the paper, but if anybody's interested, and I'd actually just revisited this package this week in trying to follow up on some active inference kinds of threads, or at least like some old approaches to EEG modeling, multi-channel modeling, that also take this same kind of physics approach, even though they're not trying to do. It's not an EEG approach where it's like trying to solve the biophysics. It's an approach that really tries to use these same kind of mathematical arguments about the relationship, that like immediately putting the data into a 64, if it's 64 channel data, like into a 64 dimensional space, and doing things like that. Anyway, if anybody wants to play with it.
Yeah.
Yeah.
But yeah, that's all. I will. That's all I had to say.
All right.
Thank you for that, Morgan. I'll look into the repo you sent.
Okay. Yeah, thank you, Morgan. That's great. So yeah, this is Quantum Compute for Computational Cognitive Modeling. It says this library makes that isomorphism computational, which I guess is like this. It's going from spin glasses, and this is in material science, to social science, where we're looking at multi-agent systems, social optima, which is characterized by the Nash equilibrium, and then things like opinion tipping, consensus dynamics, and polarization. So you're using the same Hamiltonian representation and the same tools to do this sort of thing. Then the key results, quantum minority game interference reduces herding by 90%. So it uses quantum interference in strategy selection. It has this mapping between materials, science, and social systems. So if you have different spins in the spin glass, up or down, that corresponds to agent opinions. So the different states of agent opinions. There's a coupling, a ferromagnetic coupling and an anti-ferromagnetic coupling in materials systems. And in social systems, this is conformity, which is agreement incentives, and competition, which is disagreement incentives. You have disorder, which is corresponds to heterogeneous social relationships. You have temperature, which is of course a single parameter T, which is bounded noise and rationale, or bounded rationality and noise into social systems. You have a ground state in material systems, whereas in social systems it's the Nash equilibrium and social optimum. And then there's the spin glass phase, where the social system analog is polarization lock-in without consensus. And then phase transitions in material science with the parameter TC is corresponds to the tipping point in public opinion of social systems. I think in Wednesday's meeting, I think Avery and myself, we had this discussion about spin glasses and things like that, if I recall. And it was like kind of talking about some of these analogies between, and in this case, they were trying to understand allostatic kinds in the context of the paper that Jesse was talking about earlier. So, we were talking about that paper and some of the abstract models that they have for networks and for lattices. And then, they asked me, what, how does this map to like a set of social interactions? So this is actually very useful for that as well, because it raises those analogies, between different things going on there.
Yeah. Sorry about the echo, but yeah, just I think it is really interesting the social physics relationships, and there is a review paper that I have in the README for the project. That's nice overview of the field.
I'm very curious to look at social physics as a means to look at some of these things, because it's an area that I feel like I've known about indirectly but haven't really engaged with in terms of both, especially computationally, and then also in general at that level. So I'm absolutely, I just mentioned it to Avery in the Joe Pro Discord, and we'll follow up with that for sure. So thank you.
And this it seems kind of theoretical, but it's really interesting when you think about the people who work with the like super large data sets, like all the data from Twitter, and you can actually get some really interesting physics phenomena, or like it's actually very useful for them to see the data sets with these physics analogies.
So this is Morgan's repo. Is there like some documentation I should be looking at for or is this the documentation you were referring to?
Yeah, that's about all the documentation. It's the documentation with some references with some more complete. So the social physics paper is at the top there.
Yeah, this is sociophysics models inspired by the Ising model. Actually, that might be something interesting to look at. So this is Pratik Mullick and Parangama Sen. This is from the arXiv. And so the Ising model, originally developed for understanding magnetic phase transitions, has become a cornerstone in the study of collective phenomena across diverse disciplines. This is this universality we were talking about earlier. In this review, we explore how Ising and Ising-like models have been successfully adapted to socio-physical systems, where binary state agents mimic human decisions or opinions. By focusing on key areas such as opinion dynamics, financial markets, social segregation, game theory, language evolution, and epidemic spreading, we demonstrate how the models describing these phenomena, inspired by the Ising model, capture essential features of collective behavior, including phase transitions, consensus formation, criticality, and metastability. In particular, we emphasize the role of the dynamical rules of evolution and the different models that often converge back to Ising-like universality. This is this universality idea. We end by outlining the future directions in sociophysics research, highlighting the continued relevance of the Ising model and the analysis of complex social systems. So yeah, this is a nice review, I think, of that whole enterprise. And this is, this goes back. You mentioned the Twitter data that people use. Oh, that got destroyed when they removed the API access. But I'm sure there are other platforms you could use for this type of research. Basically, the idea is you have like a data set. You have a data set that's like ready-made for these interactions. So the decisions for what to look at are already been made for you. It's kind of prepackaged, so you can just take you take the API, you point it at the database, and you say, these are variables, and we can just kind of go from there. You don't have to make hard decisions about what it is that are actually the important things in the interaction. Although
it's sad though. Like we've lost some amazing data sets of real social interaction. Yeah. And now these hypergraph network data sets are like old, Amazon recommendations and things like that. They're just not the same.
Yeah, I know. Right. All right. Yeah, so that's great. Thank you, Morgan, for bringing that up, because I think that was very useful.
When you this is something that I want to articulate to people who, like some of the younger people in data interaction. Like, what I want to ask this on behalf of them. Like, so when you say we've lost those things, we've lost those data sets, and the interactions have changed. Could you elaborate on what that means?
Yeah, I mean, most of the big social media companies have cut off even researcher access to their data.
Yeah, and when was there like a specific turning point for that, or does it sort of evolve as that become more and more and more propriety, and they've just cut the access down over time?
It's when the lawyers took over.
Yeah.
So Facebook's Meta legitimately got worried that they were going to have their data used against them in lawsuits, and both about advertiser manipulation and false claims about the efficacy, and of course, I think worried about the effects on minors. And then we all know what happened to Twitter.
Yeah.
Yes. So, okay. Thank you. That's something that I think, because even in data interaction, we went over like the stochastic pairs paper loosely, and just because like some kids like, oh yeah, I heard about that term, and then for those that, like even me at the time, I'm like, oh well, that's interesting. There's a paper component, what the paper is trying to get at, but it's also the social context of that time, and how like the sort of evolution of that space. It's very interesting.
Yeah, it's sad though, right? I mean, yeah. So they cut off academic researchers. They did not cut off national security access. So we still, yeah. So I learned this from the latter, and and it's like really interesting data.
Yeah, I find it rich that like they don't want their data used against them as an organization. When, but anyways,
yeah, but it's effective. It's effective national security data in the sense that like we can predict things about mass action from the dynamics.
and of course, mass action is a physics term. You know, like that's been a thing like in like the
So no, go ahead.
I don't want the echo. Yeah.
Well, I was just going to say that criticality is a physics term, right?
Right.
But like like again, you can see it in lots of social relations. Yeah.
Yeah. Yeah.
When the data set is big enough, and yeah.
Yeah, that's the thing. You need large data. You need large scale data to see this sort of stuff. So that's why everyone wants to use the APIs and things like that, because it's a ready-made source. It's not just been pre-selected, but it's also large enough that you can, find the phenomena in it.
Yeah, it is. I think the material science aspect is also actually really interesting too. And finding, it's a really rich domain for thinking about and learning about multi-scale phenomena, and what that translates to in terms of real world material science.
All right. So I think it was last week or the week before this last week. In Cognition Futures, I think Jesse mentioned this Substack post. This is why we don't get complexity. Stafford Beer, requisite variety, and systems thinking. And this kind of relates to the thing we were doing with the Evergood regulator theorem, because one of the sort of key components of the Evergood regulator theorem is this term requisite variety, or this concept of variety that Ashby poses. And the idea is that systems need variety to be sort of robust or to be adaptive. And if there isn't that variety there, then the response is brittle, or at least in terms of the model has to recapitulate the variety of a system. And if the model doesn't do that, then the model is brittle. So this is something to think about with respect to large language models, especially. Do large language models have requisite variety or sufficient variety to model the world? Because you think of language as the system, or human communication as a system. Large language models then have to have the requisite variety to respond to that, or to match that. And that's, of course, what we call an isomorphism. So the isomorphism is where the model can match the system's behavior. And when you don't have that matching, you don't have that isomorphism, when that breaks down, you end up with hallucinations, or a model that can't really give an appropriate answer. And so this is, again, it's all analogical, but basically, you can, I think this concept of requisite variety fits into that discussion. And so this is kind of an article talking about the broader enterprise of complex systems, talking about Stafford Beer's research. Of course, Stafford Beer was a cyberneticist, developed the CyberSyn project, did a lot of stuff with organizational cybernetics and applying cybernetics to organizations. He designed this elaborate model of sort of an embodied model of the organization, where the organization was sort of like a brain interacting with its environment. And so, wonderful thinker and systems level thinker as well. So this is where this post is coming from. And the reason I wanted to bring it up is because I think it does fit into a lot of these themes. So this is, this discussion is, this week I read a fascinating political discussion on an adjacent topic from Dan Williams at Conspicuous Cognition, in which he contrasts the views of Walter Lippmann and John Dewey on, paraphrasing, how politics should handle the ignorance of voters. And then, there's an example here. And then kind of getting at what Stafford Beer said about these kinds of things. Stafford Beer had this concept called the attenuation of requisite variety. So, of course, Stafford Beer was operating after the Evergood regulator theorem paper was published in 1970. I mean, he's doing things in the 70s and 80s. And this idea is attenuation of requisite variety, meaning that, it's not enough just to have variety or to have the appropriate variety for the problem. So if you have a system and the system exhibits variety, then you need to be able to match the things that are happening in that system with an appropriate response by the model. So the model has to have access to most of or all of the states of the system, and in order to match it, obviously. In some of the work we've done on thinking about this, we kind of refer to as aliasing. So the idea is that in system or in signal processing, you have this concept of aliasing, where you sample, say, like a video at a much lower frame rate than the action is happening. So the action's happening at, say, 60 frames per second, and your video is at the resolution of 20 frames per second. Well, it doesn't sort of capture the entire animation. It captures kind of like cuts of the animation. So it sort of blends the animation together, and you don't get a proper view of the action. And so it is with the number of states you have in your model. If you have too few states in your model, you alias your sort of what your model is representing and the output. So you're not getting a full representation. You're having to blend in, fill in different states with sort of an average state, and it's not, the kind of output that you would like. You have it in the other direction as well, where you have you're sampling too much of the system. So the system might have, say, 4 or 5 states that are of importance, and your model generates 200 or 300 states. And so you're sort of creating states where none exist, creating distinctions where none exist, and that can be a problem as well. So, there is this sampling issue between the model and the system. And then attenuation, of course, is interesting in that context, because you're attenuating that sampling process, or attenuating the sampling rate. So in Stafford Beer's mind, attenuation of requisite variety is the following. Cybernetics is about feedback loops. So it's where you have a system, and you build a model from that system, and you sample that system to inform the model, and you sample that system to update the model in its current state, And you keep doing that in this feedback loop, and you try to do it at the right rate with the right number of states. And if you don't, then you end up with these kinds of problems. So cybernetics is about feedback loops, providing information back to the system about how things are working or not working, whether the environment has changed, and so forth. Okay, so that's something from Stafford Beer, an observation about that relationship between the system and the model. So what these posts have in common is that in both cases, and this is talking about this post by Dan Williams, and then this other post by Henry Farrell, where Henry Farrell talks about cybernetics as the possible science of the polycrisis. And I don't have to mention what the polycrisis is. You can figure that one out on your own. So those two posts and thinking about Stafford Beer's views on requisite variety. So, basically we're trying to figure out how to manage complexity. That's what we're trying to do here. We need to be able to simplify and adapt and stabilize social systems without turning to some sort of top-down control, like authoritarianism or fascism. So, there's a temptation in, thinking about social systems to say, well, if we just control it from the top down, and this is actually true in managing organizations too, not just in politics, but, there's this temptation to think, well, I can just manage things from the top down. If we have good hierarchical control over our organization, then everything will be good or orderly. And, a lot of organizations will do this where they, have strict rules from the top, or they have 30 managers. And each manager is supposed to impose order in different ways. But the only thing you really end up with in a case like that is employees have to report to 30 managers. And nothing gets done because it's paralyzing the organization when in fact, and it doesn't even work, when in fact what you need is to have some system of sort of localized, decentralized control, and then some other mechanisms from the top down to manage that control. So this is something that is not a new problem. This is something, in fact, in organizations we've dealt with for years and years and years, and thinking about how to make those organizations as effective as possible. Okay, so that's kind of thinking about this. In the first post, this problem is presented as the paradox of the democratic process, in which unskilled humans are asked to lend their vote to complex political strategies about which they know nothing. Williams is concerned that this opens a door to simple storytelling by populists. Meanwhile, Farrell concerns himself with the problem of fixing the sprawling, complex labyrinthine mess of U.S. public services. This week, there have been a lot of attempts to make things better in simple ways, or at least claims to make things better in simple ways. And sometimes, these things get broken by thinking about them too simplistically. So, this is a pop-up, and I hate this. But basically, there are a couple of rules. So basically what this post is getting at is that there are 5 sort of rules for managing complex systems. And so the idea is that complex systems is one in which the parts are recombined to create lots of things. So you have, say, 10 states or 10 sort of parts. And, they don't just make 10 things, they make maybe 100 things or 1,000 things if they're reconfigured in different ways. And so sometimes systems have a great amount of complexity. And so when you have that kind of complexity, you have to think about every eventuality. You have to have, contingency plans for every outcome. And that's probably not possible using a top-down technique or set of techniques. So if you're a manager and you're trying to manage your team, and your team, you maybe have 10 members of your team, and they're doing 10 different things, that's a lot of combinations of things that can go wrong, or things that happen in the team. And so if you're thinking about this in terms of a very strict top-down approach, then you have to have eventualities for all those things. You have to have a program for all those things. And that can take a lot of effort just to come up with that, much less to implement it. And the problem there is maybe it doesn't even help you, because when you try to overspecify your system, you don't allow for spontaneous things to happen. And so that's a complex system. A complex adaptive system is one in which the parts can self-organize into a lot of different things that are in a way that's adaptive or that can improve things. So, a complex adaptive system might be like a living system, like an organism, or it could be like, a team in an organization where you're self-organizing your workflows and your interactions into ways that improve your performance. Okay, so and then there are these rules of systems thinking. So rule number 1 is parts combine to make the whole, and you can't necessarily look at that in a inherently reductionist way. You have to look at the parts as parts, and then the whole as the whole. So, it's very much the idea that you have this emergent structure that kind of is the outcome of interactions. And then it's a distinct thing from just being a sum of its parts. And so then that's rule number 2. Parts come together at distinct time scales or length scales. So you have things like a leaf, that's part of a tree, that's part of an ecosystem, that's part of a planet. And at all those, or planetary ecosystems, at all those scales, they're very different. So you can't just say a bunch of leaves make a tree, a bunch of tree makes a forest, and so on. Rule number 3 of systems thinking is that emergent pathways become more complex over time. So this is because they have more doors to open within them. So as you kind of have your system and it's evolving, it's moving from state to state, and it's, that's that in and of itself. You have like maybe 1,000 states, but now you have these pathways that go from state to state. You have these chains of events, and you have these contingencies. So if I move from state to state, it's not just that I visit one state and then another state and then another state. A lot of times I have branching events where the system will go off into 2 states given any sort of thing that happens. Some critical event might happen that could drive us down one path instead of another. And so, understanding how to make decisions in that environment are very hard to do from the top down. Rule number 4 of systems thinking is that we can look backwards. That we can look backwards through the things that we have passed through, but it is really hard to look forwards. So this is this idea of inverse systems. So like if you think about maybe a structure like a termite mound, it's very easy to sort of trace that process forward. If you're modeling this, say, in an agent-based model, or if you're just observing a termite mound being built, you can trace the interactions of the termites and how they build the mound. You can do this with wasps' nest as well, and I covered a paper on this in DivaWorm, I believe, a while back, where they kind of study different wasps' nests and the topology of the wasp nest. And the idea is that wasps will carry little balls of mud and deposit them in different places and build the nest. So it's very organized and very ordered, but the design is variable based on, these different individual actions. And so the different individual actions actually are based on prior collective behavior. And what you can do is you can trace out or predict the forward process. So everything going forward, I can say, well, this set of interactions happened to build this thing. The thing you can't really do very well is to go backwards and trace back those actions. because as it turns out, you can observe something unfolding, but it's very hard to go backwards in time and sort of infer. So you can predict maybe individual actions, but you can't infer them. And that's because these individual actions are different every time that process is set in motion. So for every time a bunch of wasps build a nest or a bunch of termites build a mound, they do it in a slightly different way. And so you can observe the forward process, but the backwards process is much harder to infer. So that's rule 4. And then rule 5 is where systems pivot around stable attractors until they don't. So there's a lot of stuff on attractors and their role in, in popular science and in sort of this fashionable mode of thinking about all systems in this way. So this is, the idea that you have stability or you have these stable points of a system, of a self-organizing system, that can maybe shift over time or become suddenly unstable. Or, we don't really understand the conditions under which attractors form and attractors sort of become irrelevant, or systems shift into new attractor basins. But that's critical to understanding the global state of the system. So that means that if you're dealing with a politics or decision-making scheme, then you have to know kind of the things that are most efficacious for changing where you are. And this is, I think in a lot of governmental policy, this is a big thing because, if you want to control something like inflation, they have different levers that you can use. I mean, economists have different levers they can use to sort of affect inflation, to make sure that inflation isn't running too hot or, that there's deflation. But overall, I mean, they have those tools, but then it's limited as to what the effectiveness of those tools are. So sometimes you get into a situation where it's hard to control the overall rate of inflation just based on those tools. And, the actions are kind of like sticking, poking the system with a stick and hoping it'll respond in the way you desire. And, that's sometimes it doesn't work very well. And it's not the fault of the policymakers or the actors, it's just because it's a very complex system. So these are these rules, and then the author here goes into this anecdote about creating a little tribe and how it maps to this sort of model of complexity. And then complexity is about trying to understand the future. Simplicity is about trying to understand the past. Experts / technocrats and historians are very good at understanding the past, but not so good at telling us about the future. In truth, it's not really fair to call interpreting the past simple, but it is simple in the sense that it is knowable. So simplicity is really kind of a thing about knowledge. So, when we talk about complexity, we're talking about things like emergence, or we're talking about things that don't have a strict cause and effect. Like if we manipulate something, the outcome isn't always the effect, a very strong effect. Sometimes those effects are attenuated. Sometimes they don't happen in a linear fashion. So if something is knowable, it's easy, it's simple, right? If you know something is going to happen, you can rely on that, it's simple. If not, it's complex. And so this is where this distinction comes into play. And then now Stafford Beer wanted us to understand systems so we could better manage variation. So again, this theme of variation comes up. Variation is just a fancy way of saying change. I mean, it is change, but it's also like diversity. I guess variety is sort of the number of states that you have, a number of different states that you have. So if you have a bunch of states that are generally similar, that's something that's easier to say control or know than if you have a bunch of states that are sort of all over the place, that they're highly diverse or highly divergent or heterogeneous. And so this is just basically, variation is a fancy way of saying change or novelty or difference or stuff that doesn't fit the learned patterns, rules, and technologies. Unfortunately for 2025 humans, this discipline was christened cybernetics, and then it just became kind of a science fiction curiosity, although I don't know if I'd agree with that. I think it's just kind of, the term is more powerful than, or more legendary than the actual techniques developed underneath it. And this is annoying because cybernetics just means steering of a system. So the steersman analogy of kybernetic or steering of a system. So that's all it is. It's just about how do you control a very complex system. And it's very different from controlling a simple system. So if we stop calling it cybernetics and call it coordination, we might be more able to wrap our heads around it. And so when a stable system experiences variation, it must adapt or die. And then, so this leads us to this rule number 6, and that is evolution has developed a toolkit to help organisms adapt to challenges or experiences in variation. Many involve rule number 1, which is parts recombining. We tend to call this cooperation and dismiss it as a rather flimsy and weak premise. It isn't. Recombination of parts, coalitions, cooperation are how we went from being bacteria to big brain complex apes, I guess. According to Stafford Beer, the key to dealing with variation is to meet it with an equal and opposite amount of variation. The law of requisite variety, which is, of course, this distinction between the system and the model. So if the system has a lot of variation, the model needs to have a lot of variation that counters that, or to matches that, is a better way to put it. Controlling variation, then, is described as variety attenuation. So being able to control variation and say, this is the mapping of variation, but then all these variants, we know kind of what to do in every, we don't know what to do in every case, but they're different sort of mean responses we can give that kind of cover our bases. It's a kind of a distinction that's interesting because, the claim here is that we can control complexity. So we're doing the same thing we're doing for the top-down case, except we're doing it in a different way. And the question is that really a thing we can do? Or is it just simply that some systems are so variety-filled and chaotic and complex that we can't control them no matter what? And that, of course, is the whole idea of chaos. And aside from the sort of the pop culture shorthand, there are systems that operate sort of on the edge of chaos, and they're extremely hard to deal with, even in this way. So this is kind of, again, a lot about systems thinking and requisite variety. And the point about requisite variety is that these parts need to cover enough decision space or action space to attenuate the novelty. So the variety, again, has to sample from all parts of this space of possibilities to be able to sort of get your arms around it and respond appropriately. So, and then this is a little bit about Daniel Kahneman and Cass Sunstein publishing some work on informational noise. And then, of course, using the term noise is just another word for variation. This is the diagram from their work. So this is where you have this combination of bias and variation. So, of course, in the world of cognitive science, we talk about bias, which is where something is favored or disfavored. So you might favor a certain idea or a certain response, and that's bias. So there's this combination of bias and noise. So in the upper left-hand corner of this diagram, you have something that's biased with little variation. So everything is clustered together. There's very little noise, but there's a lot of bias. And the responses occur all in this one part of the circle. And then at the upper right, you have noisy, not biased. So it means that the response is all over the map, all over the circle, but it's spread out. At the lower left, you have noisy and biased, which is where the responses are spread out, but they're over on one side of the response space, covering just a small part of the circle. And then not noisy and not biased, or precise, which is where you don't have bias, you don't have noise, and so your responses are all focused towards the center of the circle. So that's what I mean by precision. And so that's, kind of this very cognitive science view of responding and attenuating variety. So this is, again, this is a circle. And it's just like suggesting that you can do this just if you have the right response to the circle. I know that's not really the point, but it does seem a little bit hard to map to practice, let's just say. So the problem is that you have different circles that maybe represent different problem spaces, and maybe the problem is that we're operating in a problem space that has different contexts. So, we can think about experts and the voting public in the case of politics operating in different circles. And so we're trying to target something in the first circle, whereas in fact the second circle is not being paid attention to. So that maybe suggests that we need to attenuate noise, but we also need to think about how biased our response is. Okay, so then this is kind of going on here, and there's this work called super forecasters, which is this idea that you can sort of predict the future better if you know kind of the right methodology or the secret sauce to doing so. So it's just, this is, again, a lot of this stuff has been around for many years in different forms. So people have made these suggestions before. This is nothing new under the sun. It's just kind of reminding people periodically that this is, in fact, the way the world works. Okay, so that was a great post. Thank you, Jesse, for introducing that to us.
Yeah, I'm glad you went through it. There's some things that may come up there, and both to mention with Avery and also some of the Cognition Futures or cybernetic stuff in general. I feel like I have a number of follow-up questions to explore, but I'm going to think about them before I get into them. But thank you for going through that.
I think there's a lot of stuff. I mean, one of the things is that we kind of talked about this in the EGRT paper. So we talked about this mapping between the system and the model, and then this idea of this feedback being a key part of that, the number of states in your model and in your system being a key part of that, and then this idea of emergence or emergent phenomena where we have things at one scale that are distinct, and then at another scale they're inadequate to describe what's going on. So you have these emergent phenomena which come from the interaction of parts, and then that interaction of parts produces new states that we don't have in our model, perhaps. Those sorts of things. Yeah.
Yes.
Yeah. Okay, yeah. So, hello, Erin. I see Erin is here.
Oh, hi.
Hi, how are you?
Good.
Right.
Just waking up and doing this.
Oh, yeah. And welcome, yeah. So I think that's all for that. I did want to talk about one more paper, though, before we go. And this is something that I found from the journal Neuron. This is the Simons collaboration on ecological neuroscience. So now we've talked a lot about ecological psychology in the group, and how that's distinct from your typical psychological approach. And then there's ecological neuroscience, which really stresses the sort of external validity of the experiments. That is, like, if you do a typical experiment where you have a control group and you have like these trials that you present, that's a great way to sort of get at the mechanisms behind what's going on in the brain, but it's not a great way to understand like real-time behavior or behavior in the real world, which can be quite different. And so the Simons Institute has been doing, they have this team in ecological neuroscience. So this is where we're studying how the brain interacts with the world. And this article is from a number of people here. I'm not familiar with any of these people, but we'll see what the paper says. The Simons Institute in Ecological Neuroscience, or SEEN, which is the acronym, seeks to uncover general principles of brain function through an ecological perspective, studying perception, cognition, and action in the context of the affordances available to different agents. Here we introduce SEEN's goals, hypotheses, and approaches, outlining a collaborative vision for the next decade. So this is sort of setting up what they're trying to do here in this project. And so this is just kind of, I guess there's some results, but it's mostly a vision that they're trying to state. But let's look at what they're doing here. So, they basically set this up as like, this kind of naturalistic neuroscience that is more attuned with what we do in the real world than sort of the typical laboratory experiment. So there are a couple things enabling this at this point in time. The first is that you have a lot of imaging technologies or other neurotechnologies that allow for a lot of sort of access to different parts of the brain. So there are different types of recording devices that operate at different time scales. I think I showed that figure, I think it was last week, of how we have these different technologies that cover different time scales of cognition. So you have EEG, you have MEG, you have single cell recordings, you have fMRI, and they cover different time scales but also different spatial scales. And so the idea is you can combine those technologies to know more about the brain than you otherwise would. But then also we have this miniaturization, so you can take this and make it mobile. And so then you can actually be, you can get a better account of what animals are doing as they're freely moving around in an environment. They're interacting with things. They're grabbing things. They're walking or running. They're interacting with each other and so forth. We can also do things like tracking of movement. So we can actually track movement where, that's sort of the behavioral output. So you can look at the outputs of neural dynamics as behaviors. And so that's kind of the idea here. And so these technological leaps allow us to sort of build this research program and answer questions. And answer why questions instead of just how questions. So how questions are really kind of best answered with reductionist techniques, if you're looking for a mechanism, but the why questions maybe require a different approach. And so this is where we get into the SEEN project. And their definition of ecological is perhaps not the same as what we have from the J.J. Gibson definition onward, which is to say that J.J. Gibson had a very specific definition of ecological. But there is a sort of a focus on naturalistic approaches here, which is sort of what J.J. Gibson was getting at with his view of ecological. But this is, it's a naturalistic approach. It's where instead of having individual discrete trials and then averaging over trials, you have a run where the subject is freely moving around. You build a trajectory of behavior, sort of a trace of neural activity, and then you match those up. And you can then, you don't necessarily take the average of the behavior, but you're taking the dynamics. You can average parts of the dynamics together, but the idea is that there is this this ability to look at things in a temporally dependent context. So that's kind of thinking about how they view ecological as naturalistic, but also that you have these naturalistic stimuli. So, you have things like fluttering leaves rather than random dot kinematograms. So in the lab, we'll use these very highly abstract mechanisms, and they're supposed to represent things in the real world. So you'll show people a picture of a bunch of dots or dots that cluster together versus not, and then that gives you some indication of, how people perceive patterns. But instead of doing that, we can also just give people those patterns directly, and then there is this aspect of universality versus specificity. So if I show you a picture of fluttering leaves, you can respond to the fluttering leaves, and I can get your response. Now, whether that maps to some other type of motion is questionable. But then again, if you give me a bunch of random dots, that might also be questionable as to whether that translates into any broader set of findings other than your ability to recognize patterns in random dots. So it is a question of how universal some of these responses are. But the way to do that, of course, is to do this across the number of tasks and see what the commonalities are. And it probably would work better than giving a universal test of that. But, again, we don't necessarily know that to be the case. You need to have the research program to see. Conversely, ecological tasks need not involve naturalistic stimuli or behaviors. Artificial inputs or even highly trained behaviors can be ecological, provided they embody the right organism-environment coupling and computationally appropriate challenge. So naturalistic and ecological are thus complementary, but not synonymous. So, sometimes we're dealing with ecological validity, sometimes we're dealing with this sort of external validity of a naturalistic view, and they're not synonymous, but they do enforce sort of a better practice for experimentation, if possible. Then they mention ecological psychology, which combines both of these. Sen emphasizes the ecological over the naturalistic, so there is a difference there between ecological psychology and what they're doing in this research program, but it's a minor sort of aside. I mean, it's just kind of like we're not living up to the principles of J.J. Gibson, but it's a practical thing more than a philosophical thing. So they mention that we consider a task to be ecological if it includes three elements. First is a closed loop perception action loop, so being able to interact with the environment freely, but also in this closed loop way that's not decoupled by experimental abstraction. Then two sequences of actions and a delayed reward structure create a credit assignment problem in linking actions to outcomes. So, there's this idea that, what thing in the world causes this thing to happen in the brain. And so, being able to sort of have a way to understand that and just throwing people in a naturalistic environment doesn't necessarily allow you to do that. You have to control the experiment somehow to make sure that that's accentuated. So you can have that credit assignment that's very clear. And then three, partial observability, requiring brain states that synthesize sensory inputs over time to infer hidden world variables and guide actions. So this sort of partial observability of what's going on in the brain. So we can't observe everything that goes on in the brain. We have our tools, and we can figure out what we could, from what we can measure, we can figure out different mechanisms, but we can't observe everything that's a part of this sort of brain state. So, we use this sort of these partial states, and we have hidden states sometimes that we have to sort of infer our way around. So we'll use maybe sort of a hidden Markov model approach to extract that from the data, but we can't incorporate that into the experimental design itself. We do not espouse Gibson's claim that all information needed for action is directly accessible in sensory inputs. So Gibson argued that everything you need to know about action is in sensation, and they don't sort of subscribe to that, nor do we share his aversion to the concept of a representation. And we've talked about representations and representation-free stuff, and this actually goes back to the sort of radical cognitive or radical embodied cognition idea, as to there are no representations in the brain. And of course, a lot of neuroscientists and a lot of machine learning people would not say that, that they're representations, and in fact there need to be representations. So there's this debate over representation-free cognition versus representation-heavy cognition, and they do go down on the side of representations exist. So that's kind of the idea here. And so, yeah, this is interesting. With modern connectionist models, the divide between ecological psychology and ecological neuroscience has shrunk. Neural networks can rapidly extract features from all inputs to guide behavior, blurring the line between direct perception and internal computation. That's an interesting quote, because that is kind of interesting. That we can enable sort of ecological psychology and the study of it because we have these techniques that sort of shrink the distance between what we need to observe and then this ideal of direct perception as the driving force behind action. Thus, our use of the term ecological neuroscience draws inspiration from ecological psychology, with its emphasis on perception, action loops, and environmental affordances. So this is, of course, where we have environmental affordances available to people interacting with things, but it extends towards mechanistic, neurobiological, and computational accounts that can span species and neural systems. So that's kind of where they're coming from. And so then they have these overarching hypotheses. So the first is, according to representational approaches, intelligent systems aim to infer latent causes from their observable effects on sensory inputs. By exploiting the statistical structure of the environment, internal models, or these representations, support flexible prediction, generalization, interpretation, and decision-making, and this is similar to model-based reinforcement learning. Representational learning, therefore, plays a central role in modern neuroscience and machine learning, where both biological and artificial networks can learn generative structures from data, which in turn can be used to explain and produce new observations. Intelligent systems may create a perceptual module to represent sensory information about the world, including information that is not immediately useful. Then it may use a separate policy module to choose actions based on these action and value agnostic representations. So this is hypothesis 1, encode all causal latent variables. Then we, of course, have hypothesis 2, which is encode reward predictive variables. We have hypothesis 3, which I guess is H1. And this is based on this idea of ecological psychology. So rather than developing a complete internal model of the world or narrowly reward-centric representations, our brains may be focused on representing what Gibson calls affordances, or the opportunities for action that the environment provides. Although this idea has been explored in both ecological psychology and neuroscience, it is yet to be developed into a mathematical framework. So we formalize this third hypothesis as encode or prioritize encoding of controllable latent variables, generalizing the categorical affordance, and this becomes a continuous method of controllability. So this is where we have these three hypotheses. The first is encode all causal latent variables. So everything that is a latent variable is encoded. And so that's, And then the second one is encode reward predictive variables. And then the third is encode controllable latent variables. And so then this idea of the affordance as continuous controllability is interesting, just on its own. So the idea is that these hypotheses need not be mutually exclusive or sum to one. They're sort of on orthogonal axes in the space of all possible internal representations. In their extremes, these hypotheses are already falsified. We can see the moon falsifying the extreme H1 and H2 hypotheses, although we cannot control it and it does not provide reward, at least not in the sense of promoting evolutionary fitness. We do not explicitly perceive the countless air molecules that cause wind or the billions of soil microbes that sustain plant life, falsifying the claim that we encode all causal variables. So, okay, further, it is possible that the other axes of this hypothesis space could exist, and that as animals learn to negotiate their environments, a representation that was more like HO-like becomes more H2-like. So this is kind of pointing out this idea that, like, it's kind of like this idea of ecological psychology as being the notion of direct perception. What they're saying here is that sort of the extreme position, maybe something like what Gibson took, is falsified because, you know, you don't have to touch everything or experience everything that you know from sensory inputs. So if you see the moon in the sky, you don't need to touch the moon to know things about the moon. You can you can make inferential judgments about things based on observations and other things like that. So that means, this is, you see the moon in the sky, you don't need to reach up and touch it to know it's there. You can figure it out from other things. And so that's kind of what they're getting at. They don't need to take an extreme position on some of these things. They just need to have some moderate sort of position on this. And then this plays into the representations that are built.
Can I ask a question about this?
Yeah.
I was just having having a conversation earlier today, and it's a very sidebar comment, and it's a very me comment, and I know it's sort of a probably which perhaps a large amount of things I say fall in the category of not actually being that useful, but what to put it in a very maybe even intentionally naive way, why? Well, the root of the question, and I'm changing it as I go. The root of the question is essentially, the sense that Gibson's and perhaps extreme, take about its direct perception is that version of things. But either in understanding Gibson's viewpoint or people after it, how can I say this the right way? A very poor version of the question is it not the case, or is it, I guess, why haven't, I don't even know how to say this, basically along the lines of why compete, why uniformities, why does it all have to be one? It all has to be direct perception. And I know this, we know, we're you're doing meta brain models, and I'm sure other folks in the world have considered there's more than one kind of perception and kind of cognition happening. It's not all one magical theory that someone says, oh, it's all direct perception, But I guess how, maybe to ground it in the paper, do you see this paper as essentially trying to give space for, okay, Gibson saw it this way, we're moving in this direction. Here's a more nuanced view that has, if you will, sort of a hybridization or a better allocation of, here are some things that are for direct perception, but we also know, like we said about the moon, we can make reasonable inferences that aren't just, by direct perception.
Well, I think the reason is because they're actually dealing with the brain. Like in Gibson's case, he was not connecting neuroscience to it. It was sort of like, this is how we deal with a perceptual scene. And then in radical embodied cognition, it's largely philosophical. So from a philosophical perspective, you don't need to have a representation. But when I guess, and I don't want to say that like neuroscience is where the rubber meets the road, but it kind of is that you have these neural mechanisms and you have ecological stuff going on. You have that perspective, and you have to kind of unite them. And I think especially also with like with machine learning and so forth, that like there are representations that are built in those models. So there's some role for representation. It's clear that it's not representation free. We do things, and we have perception. We also have like decision making and memory and things like that. So we have those something. If we don't call it a representation or not, that's a sort of a academic debate. But you can't take an extreme position and do a neuroscience of ecological you know what I mean? Like you have to take a more moderate position. And it's not to say that like people who think that representations are superfluous are wrong. It's just to say that like you need to have a stand-in at least for these kinds of things.
Yeah, I think that's a very. I really appreciate that response, because I think what I'm evolving some of my macro perspectives on these things are is like, and this goes back to some core aspects of like Cognition Futures methods project. This goes back to even the first paper today about topological constraints, and it's sort of this sort of methodologies as constraints, as not a ground truth, but like the means by which your vantage point is situated against something that you can measure or push back against it. In neuroscience, you have things that we can at least measure to some degree. In machine learning models, we have some amount of we're creating the model, so even if there's black boxes, so like, okay, we know this amount of how we're making it and what some part of this representation or whatever might be. And it also goes back to, which came early this week, the Norbert Wiener quote of probably the one I cite most about the transmission of information is impossible save for as a transmission of alternatives. And like, why I'm saying it here is like the necessity to ground some of this stuff, even in a way that's not it's sort of the idea of trying to prove, and maybe it's even more a matter of like epistemological humility or epistemic humility in okay, here's what, from this point of view, and if you link this methodology, here's what you can kind of, there's a certain not mutually informed constraint in the Amanda Nelson sense, but there's a certain mutually, the constraint of the methodology offers a context window, offers a bounded context for which things you can do, what you can understand within that space, and having articulations about what those things are helps the process. Anyway, I'm speaking a bit more greedily, perhaps, from there's a project that I'm working on that's addressing what I'm saying, and I can't really articulate it much more than that right now. But I appreciate your response very much in that sense.
Yeah, it's fine. Yeah, I mean, this is just kind of like one perspective on this too. It's so. Let me finish up here and just say that, like, so that's what they're trying to do. They have this hypothesis space, and then of course they have these teams that are going to be doing this. They have 4 model organisms: bats, mice, macaques, and humans. So a good sampling of mammals, from primates to chiropterans to rodentia. And then you have the theory and data science linking all these model organisms together. So you're doing, theory building, you're doing data analysis, and then kind of bridging the gap between all these kinds of diverse systems. You have this sort of model of affordances. Let me zoom in here. So you have, of course, your agents. You have this model of neural dynamics. You have this model of beliefs or algorithm dynamics. You have algorithmic constraints. You have this belief and these neural dynamics embodied in a set of actions or in a body that does things, that produces actions through muscle or through limbs. And then you have the world it interacts with. So this is where the affordances live. This is where the interactions between actions and affordances comes into play. That provides a closed loop feedback back to neurons and beliefs. And then observations about the world, which are indirect sometimes. And sometimes it's like, so I can reach out and touch something to observe it, or I can observe it using like a passive sensory system like vision. So I can look at the moon and I see it. I don't need to touch it to verify that it's there or to verify what it does. Sometimes I need to touch it with, using affordances. Or sometimes an affordance could be something like a telescope where you can see detail on the moon through that tool. And so that's another form of an affordance and an observation. So that's kind of their model. And this is, the basic model of all studies of closed loop feedback, except now we have this sort of naturalistic view where we have, not these abstract things, but we have real world scenarios. And then, of course, we have our partially observed Markov decision process, or our POMDP model, which is where we have our beliefs, our observations and actions, our affordances, our uncontrollable world state. So we can control or manipulate affordances, but we also have the world state that's uncontrolled or uncontrollable, and then we have rewards. So if our affordances and our world state match together, we get a reward. If not, we don't. And then these rewards evolve over time, as well as the world state and the affordances, and then our own sort of observations and actions on those affordances and that world state, and then that influences our beliefs. So our beliefs evolve over time. And this is the thing, too, with the naturalistic view, is that you can build a model like this and implement it in an experimental design. So you have rewards from the previous time, from the next time, and that's factoring into your current time or your current observation. Okay, so and then they just get into how their team works and their outlook, and basically using this sort of POMDP model, which is of course something that we use all the time in different settings, in like looking at neuroscience and computational neuroscience, thinking about how we have this decision process that's based on partially observable things. You're making decisions looking at others' behaviors. You can't observe what's going on in their brain or what they think, like kind of privately, but you can observe their public behaviors and their sort of their observable behaviors. So it's the same thing holds true for that as well. It's very common to use a POMDP model in active inference. In fact, a lot of the active inferences toolboxes use this POMDP model to model the decision-making process for those tools. So you're implementing something very similar here. Okay. So we had some other things in the chat here. Let's see. Okay. So then that was the paper goals and the structure of experience. Even some old theory, Y theory X stuff and org management. That was from the thing that we talked about earlier with cybernetics. And then, there was some comments about the OgLab San Francisco event.
Apparently it went well. It was just a mixture there. Someone new I met was. It came up, and so it was a good event, basically. More you can say about that if you want. I wasn't there. Believe it or not.
It was. I think it was their kind of inaugural San Francisco event, even though they'd previously been here. But yeah, so that was really good to see, as well as it's also a small community. It was also interesting just how many people that I knew, that I hadn't coordinated with, but we all ended up at the OgLab meeting. So I would love to try and work more with them, or help them get more events going, and obviously in particular get some projects actually cooking. So love to and I got to meet what's her name in person, Che. So I will keep following up with her, but that was pretty funny because it's it was like halfway through a conversation where I was just like, did Jess just introduce us? Oh, okay, this makes sense.
That's cool. And we wanted to talk more about that, but if anybody from OgLab and such watches, yes, I was secretly hoping that some parts of OgLab would stay in Boston, so I could arrange more to do with them here in Boston, and do like another OgLab. Like the Human Augmentation Lab Summit was really nice last year, because I particularly liked the very careful interweaving of what I would say the society ethics technology branch of it, and it was well done. So Cheyenne is someone I met through the MIT Haas seminar series, and we talked about that's kind of human flourishing related anyway. So I'm glad that there's the San Francisco contingent is doing well, and I'm not. It's kind of a nice surprise of the small world of it all there. But cool, I don't think I'm going to be in San Francisco anytime soon, but hopefully things will happen there, and I'm sure the community will do nice things and grow there and all that stuff. So I just wanted to mention that because someone else mentioned it to me, and I was like, oh, I bet it went well. So I'm glad it did go well.
All right.
And all my other comments were basically just general things, change management. The last thing I said about substrate agnostic whatnot was something about Fuchs and resonance, but we can table that for next time. I feel like the Fuchs concept of resonance might help with some of the things that I was talking about before, but we're way over than I realized. So, continued on that.
All right. Thank you. See you next week.
Take care, everybody. Bye-bye.
Bye.
Take care. Bye.
Take care. Bye.